We have come up with a way to determine the shapes of molecules. But another question we can ask is this: which of the central atom's valence electrons are being shared with the terminal atoms? Another way to ask this is, which orbitals on the central atom are involved in the bonding with the terminal atoms? To answer that, we need to think about the direction in which the orbitals go and the direction in which the terminal atoms are. To do this, we'll use a theory called valence bond theory. Our idea of bonding is this: electrons are shared when orbitals overlap in space. We have seen this before when we looked at figure 5.1 from the textbook. At position 3, 1s orbitals on adjacent hydrogen atoms are overlapping in space. At position 4, the overlap is strong enough that the atomic orbitals are indistinguishable, and the electrons are completely shared in a dihydrogen molecule. If we think about p orbitals instead of s orbitals, we should reason that the best overlap occurs when the orbitals are pointing at one another. Imagine on the left that atom A and atom B come together. If atom A is trying to share an electron in a p orbital that goes left and right, while atom B is trying to share an electron in an orbital that goes up and down, they don't overlap well. In fact, the orbital on A lies on the nodal plane of the orbital on B, so they don't overlap at all. This would not lead to sharing. On the right, imagine atoms C and D coming together, trying to share electrons in the p orbital shown. Clearly, when they move closer together, the orbitals would overlap, and sharing can occur much better than in the case of A and B. This type of overlap results in what we will call a sigma bond. So what we are trying to determine when we talk about hybrid orbitals is the answer to this question: what orbitals does the central atom use to form sigma bonds? Or, which orbitals on the central atom point toward the terminal atoms? Let's start with this model that has a central atom with 2 electron groups and 2 terminal atoms 180 degrees apart. What we're asking is, which orbitals on the central atom are involved in sigma bonding? Which orbitals are pointing toward the terminal atoms? Well, all atoms have s valence electrons, and s orbitals are spherical. S orbitals point in every direction, so they can be involved in sigma bonding regardless of what angles the terminal atoms are at. Now, with p orbitals, remember there are 3 of them. There's up-down, there's front-back, and there's left-right. Which of those point toward the terminal atoms? Well, clearly the left-right orbital does. What about the up and down? Nope, doesn't work. What about front and back? Nope, doesn't point toward the terminal atoms. So just one of the 3 p orbitals points in the correct direction to overlap and do sigma bonding with the terminal atoms. Now, we need to be careful. We're not saying the s orbital bonds to one terminal atom and the p orbital bonds to the other. No, it's some combination or mixture or hybrid of the s and p that does this sigma bonding, because both of those atomic orbitals point in both directions. Let's keep track of what orbitals the central atom uses to form sigma bonds to terminal atoms. We should note that the hybridization correlates with the bond angle, which comes from the number of electron groups surrounding a central atom. If the bond angle is 180 degrees, the central atom uses its s orbital and one of the p orbitals, the one that lies along the same axis as the terminal atoms. We say that the other 2 p orbitals are left over, although we'll find in the next module that these p orbitals can engage in what is called pi bonding. So it's worth keeping track of them in our table. We would then say that the central atom uses sp hybridization. Here we have a model with 3 terminal atoms at 120 degrees apart. and we're asking which orbitals on the central atom point toward the terminal atoms. The s orbital on the central atom points in every direction, so the s orbital on the central atom can be involved in sigma bonding. Now with the p orbitals, again there are 3 of them, we'll find that one of them, which goes front and back, does not point at any of the 3 terminal atoms. In fact, the one that goes front and back, its nodal plane points in the plane of the molecule, so that one doesn't work. The one that goes up and down clearly can interact with the one on top. But what about this one here on the bottom left, this terminal atom down here? Which p orbitals on the central atom might point towards it? Well, the one that's up and down kind of goes that way, and the one that's right and left kind of goes that way, but it's really going to be some combination or mixture or hybrid of those 2 that's going to be involved in the sigma bonding along with the s orbital. To summarize for 120-degree bond angles, the central atom uses its s orbital and 2 of its p orbitals. That leaves 1 p orbital left over. We say that the central atom uses sp2 hybridization. Note that it is not sp squared, it is sp2. Here we have a model with a central atom and 4 terminal atoms where the bond angles are 109 degrees. So again, which orbitals on the central atom are involved in sigma bonding? Well, the s orbital points in every direction, so the s orbital can interact with all 4 of these atoms. Now, for the p orbitals, it's much harder to see, but let's just focus on this atom out here. It's forward, it's to the right, and it's down. So, the p orbital that goes forward, and the p orbital that goes to the right, and the p orbital that goes down, all 3 of those, some combination or some mixture or some hybrid of all 3 of those, can be involved in the sigma bonding along with the s orbital. For 4 electron groups and 109-degree bond angles, the central atom uses its s orbital and all 3 of its p orbitals. There are no p orbitals left over. We say that the central atom uses sp3 hybridization. Again, it is not sp cubed, it is sp3. Let's go back and look at our 6 prototype molecules and assign hybridization to the central atom. CO2 has 2 electron groups, so it will have 180-degree bond angle and sp hybridization. SO2 has 3 electron groups around the sulfur, so it has 120-degree bond angles and sp2 hybridization. H2O has 4 electron groups around the oxygen, so it will have a 109-degree bond angle and sp3 hybridization. SO3 has 3 electron groups around sulfur, 120-degree bond angles, and sp2 hybridization. NH3 has 4 electron groups around central nitrogen, resulting in 109-degree bond angles and sp3 hybridization. CH4 has 4 electron groups, 109-degree bond angles, and sp3 hybridization. What you should notice is that 2 groups is always 180 degrees sp. 3 groups is always 120 degrees sp2. 4 groups is always 109 degrees sp3. Electron groups, bond angles, and hybridization all go together. What doesn't correlate is the word or phrase that we use to describe the shape of the molecules. While there are only 3 possibilities for bond angle and hybridization, there are 5 possibilities for shape.